I'm Jürgen from the data science team at XING, and together with Katja, we will tell you a bit about how we build recommender systems at XING. And Katja will start giving you some of the theoretical and basic information about what we do with our recommender systems.
So good morning. In this talk, we will focus on job recommendations and how they are created at XING. I will give you an overview of the recommendation strategies that we apply, how we enhance our user profiles to make the recommendations better. And then thereafter, Jürgen will tell you something about it, how we actually make these recommender systems fast in production and reliable. So for job recommendations, the challenge is that we want to recommend job postings to our users that are actually relevant for the users. But from the company side, we also want to show job postings to these users for which they are really the appropriate candidate and the company would be interested in them as well. So currently we have about 650,000 job postings on our platform, and about 20 million users for which we create these job recommendations. And if you have a XING profile, which I assume, then you most probably already got some job recommendations. So for example, in the job market where you can search for job postings, we directly create some recommendations for you. We also have recommendations for the mobile phone if you have the XING app, and sometimes we also send emails if we think that you're really a good match. So I hope you're happy with your job recommendations. If not, come by the booth later, tell us what's the problem, and if you're happy, then please come as well, because that's always nice to hear. So we have some goals, as I already said, and sometimes they are contradicting. So for the users, we want to have relevant recommendations. Users do not want to be spammed. On the other side, we have the companies that pay us for the recommendations, and they want the best and most relevant candidates to see the job postings from their company, and they want to have a high reach. And then we are in the middle doing the match between the users and the companies, and for sure we want to have happy companies, we want to have a high revenue, so we want that the users click on paid content, but we also want to have happy customers, which is more or less the most important thing as a social platform. So in order to recommend the most relevant content for the users, we need to understand the user demands. And there are several sources that we can use for that. And one of the sources, is the most obvious one, is the explicit user profile, where the users tell us what is their current job title, their position, which company are they working for, where are they working, what are their interests, what are their skills, and so on. On the other hand, we also know who the user is contacted to and how these contacts are again interconnected. We also know the interactions of the users, so we know on which job postings did they click, which job postings did they bookmark, which job postings did we actually show to the user but they just ignored them. So, and finally, we can figure out who are similar users, for example, users with similar skills in the same job role, and what are the interactions of these users. So, and the key properties of a job posting can you see here. So for the job postings, we also have the title, we have the company, we have the location, we have the employment type, which is full-time here, we have a career level, we have a full text description, and on the end, we also know the employees of the company, maybe their contacts of the user for which we create recommendations, what are the social benefits, what is the location, and so on. So now we need to match that. And for that, we have different recommendation strategies. A lot of them are content-based. So the first one is a really basic, for which I will show a slide after this one, where we really take the explicit user profile, we take what the user told us and match that against the job postings. But the job postings, the user profiles only contain the current information, also the past information. So they contain the education, my current position, the positions before, but they do not contain a lot of information about where I want to go. So when I was a researcher, I was looking for a job position as a data scientist, but this is nothing that you could see from my profile. In my profile, I was just a researcher. So, and this is why we also create interest profiles and match them against the job postings. We also have an item-to-item recommendation. So if we know that a user really likes an item, a job posting, because he, for example, bookmarked it or rated it very highly, then we try to recommend more of the same, very similar job postings. And then we also have a kind of a collaborative filtering, for which I will also say something. So in the content-based filtering, we first of all have the user profile. So here we have Fabian. Fabian is a data mining expert with skills MNL, J2EE, in Hadoop, in informatics, education. And yeah, now we want to find the best matches. But that's all in natural language. Natural language is ambiguous. So we first of all need to understand what the user wants to say with these skills and with this job role. So we have our ontology. And this way we can translate data mining expert to data scientist. We can translate ML to machine learning. We can translate informatics to computer science and so on. And with these terms from the ontology, we create an Elasticsearch query against the 650,000 job postings that we have, get back the most relevant ones, and re-rank them according to TF-IDF. So the more keywords of our query are contained in a job posting, the more relevant it is. But on the other side, there might be some skills that are very common that do not weigh so much. So this is meant with the TF-IDF. So if, for example, 80% of the users have flexibility as a skill, and you have flexibility for the user and for the job, it's not so trustworthy as when you only have 1% of the users having Hadoop as a skill, and this is a match. Okay, so let's go to the collaborative filtering. I will first say something about the theory behind that. So here we have our four users. We have Anna, Julia, Tim, and John, who rated 5 job postings. So on a scale from 1 to 5. And in user-based collaborative filtering, we try to find similar users, which we can do by comparing the ratings. So here we can say Anna and Julia seem to be pretty similar because they both like the data engineering position at Zalando. They did not like the business intelligence developer position at Good Games. They are not so sure about the Java developer position at Telecom. So we can say they are pretty similar in what they are looking for. So, and because we think, or we know because Julia rated the job posting at XING, that this might also be a good match for Anna. On the other way, you can also compare the items based on that user item matrix. So here we can say that the job posting from Zalando and from XING seem actually to be pretty similar as well because they attract the same user. In this case, Julia and John rated both of these items and they rated both pretty highly. So again, we would recommend the XING posting to Anna because she already liked the Zalando posting, and we would recommend the Zalando posting to Tim because he already liked the XING posting. So this is the theory. So in practice, we have very, very, very sparse user item matrices. And I think in our case, it's even more sparse. So we called it ultra sparse here. So it's very common that like 99% of these fields are not filled. But in our case, it's even more because most of the items that we have are new items. So if a job posting is older than a month, usually it's not interesting anymore. So we have a lot of new items. We do not have so much interactions that we really can do a good collaborative filtering or metrics factorization approaches here. So what we do is that we cluster our users. So we aggregate the data to make the metrics more dense, and we aggregate the users based on what we know about them. So we aggregate the data scientists, the people skilled in Java, the BI developers, and so on. And then we know, okay, we know what the data scientists like, and we know what the people that are skilled in Java like, and maybe they are alike as well. And then if we know that Anna is a data scientist, we know what we can recommend to her. One thing is that the new item problem, it still remains. So that's for sure. This is why we have so many content-based approaches on the platform. So what we figured is that people really freak out if they get a wrong recommendation. This is not so bad for the news, for example. If you recommend a news article and the user is not interested, he's just not interested. But if we recommend wrong job posting, the user really feel like misunderstood. If we recommend an internship position to a manager, yeah, he thinks we don't get him. And we have a feedback app where the users can rate the recommendations and where they also can put free text in there. And we often get it, it's all caps, and people want to end their membership because we recommended wrong job postings. So we said, okay, we really need to try to eliminate these recommendations, how we call them, so the outliers that make our users freak out. So, and the first approach for that is that we say, okay, we have a lot of recommender strategies, and we combine all the results from these strategies, and now we filter them, and then we re-rank them. So one filtering that's very important is the career level filtering. We never can recommend something from a lower career level, for example. We have a less like this component. So as I said before, where we had a more like this component, we have a less like this component here. If we know that a user did not like some job postings in the past, and we have similar job postings again in the recommender candidates from the different recommender strategies, then we kick them out. We do not want to show too many job postings from the same company. And then we come to the re-ranking. So we always try to boost jobs that are from the location where the user works in, so that at least 2 out of 6 job postings are near the location of the user, because most users don't want to move. We also boost jobs from cities where we see people have a lot of contacts, so they already know some people. We also need to boost paid content in a way. So as I said, we want to make the companies happy as well. And then we have also an outlier filtering which is more or less the final step, where we really try to filter out the last recommendations that are in there that make our users freaking out. And for the outlier filtering, it's really a trade-off between killing the bad recommendations and keeping the good ones. So our approach is here. We take for each user the recommendations that are left over, like the top 50 recommendations, recommendation candidates. And then we predict a rating for each user item combination and say, okay, we only keep those recommendations where the rating is above a given threshold. And I have a diagram for this. The only thing that you really need to understand here is that the green line are the good recommendations, the red line are the bad recommendations. And this is an analysis that we did on a test set, and we found that if we kick out all recommendations for which we predict a rating that is below 2.5 on a scale from 1 to 5, we really can kill 86% of the bad recommendations and only kill 18% of the good recommendations, which is, yeah, as I said, it's a trade-off. We could also go a little bit more to the right, and then we say, okay, we kill 99% of the bad recommendations, but this would also mean that we would kill 60% of the good recommendation. So it's really a trade-off, because you cannot always know if a user will like a job posting. Okay, another thing is that even though the users share a lot of information, sometimes it's hard to understand, and sometimes the information is outdated as well. An example for that is, again, the career levels. So we have a lot of students on our platform that have, in parallel to their studies, they founded a one-person startup where they work some hours a week. And of course, they are the CEO of their one-person startup. but still we do not want to recommend CEO positions to these users at great companies, but rather entry-level positions. So this is why we have more fine-grained career levels in the back and try to figure out with some logic what is the real career level of a user. And then, and this is something where we'll tell you more about, we also have the willingness to change jobs. We have a feature on the side, it's kind of hidden, I must admit that, where users can say if they are actively looking for a new job or not. But we found that many users use that feature if they are actually looking for a job, but when they found a job, they do not change it back. So we always think, oh, he's still looking for a new job, but he isn't. And then we have a lot of other things, how we enhance the user profiles, like the core needs, where we say, okay, why is a user on the platform? Is he interested in news, or is he interested in making contacts, or is he looking for job postings, and so on. So for the willingness to change jobs, we use more than 100 features in total. Very important is the general activity, like the number of logins, the job posting clicks, and the most important thing is if that increased in the last month or in the last 2 months compared to the last year. Profile updates are really important. We found that the profile image update is a really strong indicator that someone is looking for a new job. But for sure, if someone updates his wants, has interests, or writes something more about his work experience, his previous and current positions, then this is also an indicator that he wants to make his profile more interesting and attract more people. Another thing is the duration someone spent already in a job role. So for example, which you can see in this totally made up diagram, data scientists tend to change their job after 3 to 4 years. So this is also something that we take into consideration. So how to combine these features? We decided here to use XGBoost, which is gradient boosted trees, and I will say something about that. So we start pretty simple with a decision tree. Again, we have our training set, our ground truth, we have the 4 users that you saw before, and Anna and Julia, they have a 1 in the first column, so they are looking for a new job, while Tim and John seem to be happy and they don't want to change. And we have some more features like, did they click more on job postings in the last month? Did they update their profile image? Did they read more news? And so on. And now we want to create a binary tree to distinguish between those users that are looking for a new job and those that are not looking for a new job. So one possible split would be to say, okay, did the user click on more job postings than usual? No. Okay, he's not looking for a new job. This would be true for John in this case. And yes, yeah, so maybe we have 2 that are looking for a new job and Tim who's not looking. So we can do another split here for Anna, Julia, and Tim. And so you can see with the news, you cannot distinguish between the different groups, but with the image you can. So we add another split and say, okay, was the profile picture updated? Yes, so most probably the user is looking for a new job, and no, most probably he isn't. Trees are already very powerful, but they can grow very, very big, and they tend to overfit. So you really need to be careful with that. And what we decided is, as I said, we use XGBoost, which is a tree ensemble. So in fact, we have for this problem 500 trees that are not very deep, and so they are weak learners, but we combine them in an additive way. So we first learn one tree, like for example the tree on the left, where we consider the logins per month, if they increased, where we consider if a profile image was updated, if the end of the education is near. And then we say, okay, we have that tree now, and now we learn the next tree. And we do not learn them in parallel, but really in a sequential order, so that each tree can take into account what the first tree already learned and can focus on the errors that were made. And yeah, then in production, you can run them all in parallel and just add all the values that you have in the nodes. And it's a pretty powerful algorithm, so if you have similar problem, it's worth to give it a try, and make yourself familiar with it. There are a lot of hyperparameters that you need to tune carefully to get the best results. But yeah, it's worth it. So for the willingness to change jobs, does it make sense? Yes, actually it does. So we found this very nice correlation between the willingness to change job score and the response rate to recruiters. So we found that users that have a higher willingness to change jobs actually are more likely to answer to the recruiters. And so the key lesson that we learned is from the push recommendations. So additionally to the recommendations that I showed you before, we have push recommendations. This means it's not that a user comes to our site, but that we have a new job posting. So this comes in because it's crawled or because a company, a recruiter added it through an API. And now we want to directly find the best users for this. And we find these users, and we also take the willingness to change job score into consideration. So this way, only those users where we think they really want to change a job get a lot of these push recommendations, while those that have a very low willingness to change jobs do not receive recommendations at all. And we also have a medium class in between that receive a few. And yeah, this is how a push recommendation looks like. Maybe you saw it before. There's this orange bubble that says new, and that only goes away if you click on it. And if you do not click on it, we most probably send you an email because we're pretty sure that you will like it. And what we find here is that with this willingness to change job score, we recommended 10% less job postings per user, where we in the beginning thought, oh, that might be bad. But we also found that we actually have, in absolute numbers, 5% more users who actually clicked on a job posting. So this is the key lesson. We have less noise, but more relevance and thus more clicks. So we do not need to spam our users. If we focus on the relevant content, they will trust us more and they will click on what we recommend them, which is pretty nice. And now I hand over to Jürgen, who will tell you how it's done.
So yeah, I have this one, so I'll give this maybe later for questions. Yeah, now Katja told you what the data scientists come up with these nice models and such, but as a data engineer, you hear feature and you almost immediately say, oh, damn, this is data I need to load. And now I will tell you a bit about how we are at the data science teams go about building such systems. First, few sentences regarding our tech stack. So really central, one of the major things we use is Scala. So everything in production from the REST services and MapReduce jobs and such is written in Scala, and we are really, really happy with it. Big lovers of the code quality coming out of it. And around Scala, we have a bunch, probably a lot of you are using the same things. So no big surprise there. So we have a big Hadoop cluster where all this information goes, where data scientists can go using Hive and do analysis and also prepare data, then, which is later used in the production systems. For storage, we mostly rely on Cassandra and MySQL, depending on the access pattern. Yeah, all the services are packaged in Docker. From the Scala side, we use one big library, some Play for building REST services, and Archive as a concurrency toolkit, which I would also, if you're doing Scala, probably you know it, but otherwise, they also have Java APIs, and I would recommend looking into Archive. It's really a nice piece of software. For data transformation stuff, we rely also now, since 2 years, quite heavily on Kafka, another awesome piece of software. So if you are not using Kafka and look really into it, it's really a nice piece. So one of the software systems I have the least trouble with running, actually. So yeah, so we really love data, and from the Scala world, we are really huge fans of functional programming and types. So from the top level view, if you say, okay, we have a job recommender, yeah, we do kind of microservice services in some cases. Some are really small, some are a bit bigger. How does it actually look? So if the job recommender is mostly one input, which is the user ID from outside, right? Give me the job recommendations for a user. And for the job recommender, actually we have to do quite a lot of stuff. So we have around, depending on your user profile and some other stuff, we pre-compute, we have around 20 database calls to Cassandra or MySQL for one single user lookup for recommendations. 7 REST curls to other services, and 4 Elasticsearch queries are being run. So that's quite a bit. So if you think about your normal service, so how can we actually make this work, right? So data scientists come up, oh, cool, we have this new model, and then they say, oh, damn, 2 new database lookups. And yeah, I looked some numbers up and say, okay, if we would do this in a single thread sequentially, we would run up to 12 seconds, which is definitely a bit too slow. So how are we going on and make this actually faster? So yeah, Scala has really some very, very awesome concurrency parts, like with Akka, or also the built-in future stuff. I don't know if you know any of this, but yeah. So the idea is really make it parallel. And to make something parallel, of course, you need smaller pieces which can actually run in parallel. So, and now I will try to explain you how we internally build these recommender systems. So we have there are 5 building blocks, including the merge, but 4 major ones. So something which we call the data source. This is something which just loads data, which is actually not a recommendation. So if you saw all these features before, Katja mentioned, the user profile, yeah, all the kind of auxiliary data you need to make actually the Elasticsearch queries or the further lookups in some other database. So that's what we call a data source, and they are quite specific, so you can have quite some of them. The sub-recommender is actually the thing which implements one of these strategies Katja mentioned. So there's one which does the collaborative filtering. There are some who do content-based lookups. And you can mix them up. So there might be data sources which run actually afterwards, after the merge. So you get 4 kind of streams of recommendations from these different parts. They get merged together, where you can have also an influence on how this is done. So normally we default is kind of a linear combination of the scores. So all these recommendation lists are kind of ranked by a score, and then you combine them at the end. And then, as Katja mentioned, is these filters like the outlier filter or carrier filter, which try to get rid of the things which might not be really a good fit. And then the re-rankers like say, okay, can we kind of guarantee more diversity in it, like not having only one company in there or something like that. So now we have all these little building blocks, and what actually happens, all of them run really in parallel. And it's, that's really nice, but of course you will also have some problems. So they run in parallel. Each one of these does only one thing, and this can get actually quite complex. So if you look at the job recommender, the latest version I looked up, we have 39 data sources, 4 sub-recommenders, 13 filters, and 11 re-rankers. So they're all in a way quite simple. So each one does only one thing, but yeah, it can get quite complex, and there I can't really probably highly recommend monitor this stuff. So each of these little boxes are quite heavily monitored for us. So look at the performance, and for filters it's also quite important to see how many things come in and how many things come out on the other side. So because yeah, if you introduce a bug and someone filter lets through too many or even no postings at all, that's really bad. So we monitor this. I tried to sneak in for code.talks actually one slide with some code, how this looks in Scala actually, how we put in code to build these recommenders. So this is something the developer would actually write. So kind of you have this chaining operator there with the squiggly and arrow. You have this part where the recommenders are merged together, and then you put in the filter. So in a way, it represents also a bit how we think about this, right? So it's kind of a flow of this data through these different stages. But I mentioned, so if you have that many pieces in there, how do we make sure that running these concurrently, that this actually works well? So because if the data source loads the data and a filter who actually uses this data, you make sure that, of course, this runs in the right order. And so I have some examples here. So if your data source providing some data fields A, B, C, and then you have, on the other hand, some subrecommender and filters and re-rankers who depend on these kind of things. And of course, you don't want to deploy something which you don't have the data for. So you add the filter, but you forgot actually to put the data source in. Boom, this should not happen. So this is actually checked at compile time. So there's heavily use of the type system of Scala. That it's impossible to actually compile something where the data dependency between data source and some filter or so is not met. And also what happens at runtime, if you disable, so from outside you can put some parameters. Oh, I don't want to have the location filter run or something for whatever reason. So maybe on some page you want to show some specific kind of recommendations and you want to tune it and switch some things up. Then of course you want to have it faster and automatically disable the data sources if they are actually not needed. So this happens then at runtime. This is something from our internal documentation for this. So to try to bring this, to try to explain how this actually works from time scale perspective. So time running from left to right. You have at the top the data sources which load this data, and then in the middle you have this thing which we call a context, and it gets filled up over time, right? So, and each of these components on the bottom kind of declare in the type system what they actually need. So, okay, I need a user profile, or I need a set of the interactions. And of course, to make this actually fast, you need to overlap them as much as possible. So if you introduce something like a sequential point, which is here actually the merge, you need to try beforehand to make this run as much as in parallel as possible. So immediately as the dependency is fulfilled, then some later stage can work. So here you see these DS, which for the second context, you see, okay, it's fulfilled, it needs these two, and immediately can start. So it has quite a huge overlap, while other data sources are actually still running. So this actually tries to squeeze these 12 seconds of I/O operations, other services, and computations down to something more manageable. And currently, the P99 is around 400 to 500, also depending on some other systems, sadly, currently. But this is already quite a huge compression of this time. And from the developer perspective, the only thing he has to do, I don't know, I hope you can read it a bit if you don't know Scala, is he just express all this in the type system. So he has never to put anything, so, oh yeah, I need to wait on this. So there's no additional code from the developer. He just implements one of these filters where it's more or less just a Boolean function, and he has not to care about all these things in the background with the concurrency or dependency. So here example would be that you have two data sources. One loads a profile and one loads some interactions. And in Scala, there's some kind of syntactic sugar for some, we can't call it a bean, where you define these case classes, and then you depend in the generic definition of the class there where it extends data source, you specify what it's actually providing. So this interactions context, for example. And at the consumer side with the example filter, then he also has this in context, and there you define this case class and there are these two fields in there. And this is enough to make the framework behind figure out what it needs and verifies this at compile time. This all makes sense for that we don't at runtime explode if something is not really running. And there, I can't really highly recommend, make love to the compiler. You will both enjoy it. So we are huge fans of static typing and make sure that this not breaks at runtime. That was a quick introduction about how we actually built this, and I think we are quite good in time. So I tried to look at the questions or comments on this, but we have also some microphones here for questions and comments. I can't really log into the speaker Wi-Fi, so I can't really look them. But if somebody has a question, then we have a mobile microphone. We are happy to take your questions.
My question is, how about you managing the interface between data science and data engineering?
Yeah, for our team, it's quite fluent, I have to say. So we have some data engineers, which probably would call, and some other companies would already call data scientists. So the skill set is quite overlapping, but in most projects, depending on, sometimes it's just an analysis, then it's just a data scientist involved, but oftentimes it's kind of work together to actually build this. So the data scientists also sometimes build these kind of systems or have a first version of it, and data engineer kind of helps them get it really production ready. Yeah, sometimes it's really an analysis, and data engineer then implements it, but it's really, it depends a lot on the case. So for some things, then we try to enable all the data scientists to actually also do Scala development and put this into production if they want. So it's up to them if they want to learn it. But so far, they were not able to break anything big. Any other questions? I will give you the mic.
Oh, finally. Thank you for this talk. I have one question. That is this calculation, like after it reduced from 12 seconds to something, is calculated in real time, or it's pre-calculated once a day or twice a day or something?
It's actually a mixture. So there are some things like these willing exchange job, for example. This is kind of one of the features you just load, but this is then done in the background. So this is job running on Hadoop, which exports the data to Cassandra or MySQL, and then it's loaded. So all of this is a mixture. So sometimes we figure out and some model is actually too slow. You can't really actually squeeze this already in this time slot, then of course we need to put this as a batch job or offload it to calculate it somewhere in the background in real time. But to remove this time constraint, if you look, okay, if you would make it fast enough to actually deploy it in real time with the service, then maybe the quality goes down too much. So it's always kind of a trade-off between, okay, quality, speed, and then you have to move it in an offline computation and export it. So that's also one of the reasons you have all these many database lookups. So there's a lot of pre-computated information already in there. Anybody else? I thought I saw another hand, but so still hangover, right? Cycles go too slow. Yeah, if not, then thanks a lot for coming. And the typical plug, XING is looking for data engineers and data scientists. So if something of this might look interesting to you, or you're looking for a new challenge, then we are outside there, right in front of the Cinema 4 here. Come, or if you have any questions you were afraid to ask here, also we are outside now. Come and find us. Maybe we can answer your questions there. Okay, then thanks.